point where we found the y-intercept, the x-intercept, vertical asymptotes, which in this case it's only one. Horizontal or slant asymptote, in this case we got that we had our slant asymptote. And well, now they're asking us whether the function, or rather the graph of the function, crosses its own horizontal asymptote. And well, for this all we have to do is set the original function, which is 2x 2x squared plus 9x plus 4, the whole thing over x plus 3, and set it equal to the value. Well, in previous examples we set it equal to the numerical value of the horizontal asymptote, right? That's like set it equal to 2, set it equal to 2. Well, in this case we didn't have a horizontal asymptote to set it equal. So in this case, yes, we will set it up, or we will set it equal to the value, or well, in this case, the equation or the expression that describes the slant asymptote, which is what we got from before. That is, set it equal to 2x plus 3. And as usual, the rest of the problem is solve the rational equation. That is 2x squared plus 9x plus 4. I will write parentheses over here, be careful, and times x plus 3. All right, so what's going to happen here? Well, so let's use the distributive property to simplify the right-hand side of the equation. That's going to give us an 2x squared plus 9x plus 4, and that equals to 2x times x, that's a 2x squared. 2x plus 3, that's a 6x. And 3 times x, that's a 3x. And 3 times 3, that's a plus 9. So we're essentially done with the distributive property part of the problem. So let's see if we have any like terms. And we have these two like terms right here, the 6x and the 3x. And they both add up to, well, number one, 2x squared plus 9x plus 4. In other words, the left-hand side remains the same thing. All we do is combine like terms on the right-hand side. That's 2x squared plus 9x plus 9. Now, check this out. Check what's going to happen in this case. So number one, notice we have a 2x squared on the right-hand side and on the left-hand side as well. So they both cancel out. Likewise, these two 9x's are going to get canceled out as well, and we are going to get with something pretty weird in here. So what's that? 4 equals to 9. Well, 4 is not equal to 9, all right? So that means we have a contradiction. Therefore, no solution. Which at the same time, this leads us to conclude f doesn't cross its slant asymptote. All right? And in this case, well, how about we make a quick note over here in instructions and change to slant? Because in this case, we got a slant asymptote, not a horizontal one. And in this case, this slant asymptote is actually the one that we got in the previous step last time. So now I think we have roughly some information to give us an idea of how the graph of this is going to look like. We have a vertical asymptote, we have a horizontal asymptote. We already know that the graph of the function doesn't cross its, well, in this case not horizontal, but rather its slant asymptote. So that's already something. Let's check for symmetry. So let's see. F of negative x, that is, replace every instance of x in your given function with negative x. If the output is The original function, again, that means the function is even. In other words, the function, geometrically, the graph of the function is going to be symmetric about the y-axis. But otherwise, if we get the opposite of the original function, then the function is odd, which in this case it tells us that the graph of the function is symmetric above the origin. That is, rotated 180 degrees, you will get the same graph again. All right, and in the third case scenario, you didn't get the original function nor its opposite, so then in this case it's neither even nor odd, so there's no symmetry at all. Let's find out about this one. All right, so 2 times negative x squared plus 9 times negative x plus 4, and then divide the whole thing by negative x plus 3. And let's simplify a bit. So that's 2x squared, because in this case a negative quantity squared remains back to positive, but it's not the case on the second term. Minus 9x plus 4, and in this case negative x plus 3. And if we compare this function, right, or this expression right here with that corresponding to the original function, we can see that this is not the opposite of the original function, and it is not the same original function. So in this case, it's neither even nor odd. And you know the implications of the evenness or oddness of a function. And you know the idea about the corresponding symmetry. So no, we're not going to have any symmetry at all for this function. All right, so let's see what's next. Determine the behavior. Oh yes, the behavior, the usual. So in this case, let's see. Number 1. So we got a vertical asymptote, one of them, and we got 2 x-intercepts. All right, so just the same way we did with the other examples, we're going to draw a number line, and we're going to put solid bubbles for those x-intercepts and open bubbles for vertical asymptotes, and we are going to choose test points in this case. All right, so let's see. So as x-intercepts, we got -1/2 and -4. And as a vertical asymptote, we got -3. So we're going to start with the vertical asymptote. That's the smallest value. Again, we draw them from, or we plot them from smaller to large. So -3. Solid bubble for one of the x-intercepts, which in this case corresponds to -1/2. Oh, hold on, there's another x-intercept that is way smaller. It's -4. And we're ready to draw the number line. And then from here, we are going to choose test points, test values. All right. So, and again, pick your favorite numbers. I'm going to pick number -5 in this interval. A number between -4 and 3. Well, here is where it gets a little weird, because we usually try to get integers to make our lives easier, right? So, but in this case, since we are working on an interval between 2 integers, well, unfortunately, there's no way around. We will have to choose a decimal or a fraction. Well, I'm just going to go with a decimal actually, and I'm going to go with -3.5. You could do -3.1, -3.2, but I think decimals, well, ending on a 0.5 are easier to work with. Or, I mean, you're going to use a calculator, but doing the homework, any number should be fine. And how about -2, between -3 and -1/2? And I'm going to use, well, there's a bunch of numbers here that we can use. I'm going to use 2, because I think we already did 0 for the intercept, so we don't repeat calculations. So let's use these test values. Let's go ahead and Plug in the values. Again, like I did before with other examples, I'm going to show one calculation. And for the rest, I will just give you the order pair. So f of negative 5, that's going to be, where's the function? 2 times negative 5, quantity squared, plus 9 times negative 5, plus 4, and divide that by negative 5 plus 3. After simplifying all these numbers, we should get negative 4.5. And well, in this case, that's going to give us the order pair negative 5, negative 4.5. We're going to do this essentially the same with the remaining test values. That is f of negative 3.5. Whoops. F of negative 2 and f of 2. In each case, well, the outputs we obtain is 6, negative 6, and another 6. That's going to give us the following order pairs. And it's important to write down these as order pairs because ultimately we are going to use these additional order pairs to get a better sketch of our graph in this case. All right, so let's write them down as order pairs. That's a negative 3.5, comma 6, negative 2, comma negative 6, and 2, comma 6. And we're essentially done with all the information that we can extract from the actual function, so we can use it to draw a rough sketch of it. All right, so let's see. So we started with the vertical asymptote at x equals to negative 3. It's denoted with this open circle, all right? So let's do that. So at negative 3, there is a vertical asymptote. Which I'm going to draw in red and also dashed. There is another asymptote that's actually a slant asymptote. But notice the slant and the asymptote, it's no longer a horizontal one. It's rather a linear, it's denoted with a linear function. So in this case, well, let's go back and refer to that equation. The equation 2x plus 3. Let me write it down again. Y equals to x plus 3. So all we have to do in this case is draw a diagonal line using the y-intercept and the slope. Well, of course, there's many ways to graph linear functions. You can make a table, plot values, etc. I mean, that's a bit time consuming, but if you feel more comfortable doing it that way, then that's fine. However, using the properties of a linear function such as the y-intercept and the slope, which is the number that multiplies the x, is going to be a lot shorter. So this independent term, the number 3, which that's denoting the y value of the y-intercept in this case. So let's go on the y-intercept to the number 3, and then from there the slope, which is 2. This is the same as saying 2 over 1. The reason why I write it as a rational function is because recall the definition of the slope. The slope is the ratio of the rise to the run. That is, rise to units and run 1 unit. That is, from the y-intercept, I'm going to go up 2 units and draw and run 1 unit. Again, repeat the process, go up 2 and go to the right one. Now, how do we go the other way around? Now, this 2 over 1 is the same as saying negative 2 over negative 1. That's another way to interpret the slope. This way, so we can go backward, or we can go down 2 units and backwards 1. Down 2 units, backwards 1. Down 2 units, backwards 1. And so on and so forth. And no matter how you do this, you will get all the points aligned on the same line, all right? So, and this is how a slant asymptote is going to look like. All right? In this case, the slant asymptote crosses the vertical asymptote, but it doesn't cross, as we found out, it doesn't cross the function itself. All right, what else do we have? Y-intercept, that the y-intercept of the function, careful. The y-intercept that we did before is a y-intercept of the slant asymptote, not of the function. So be careful here. That is 0 4/3. And 4/3, that's roughly 1.3, right? I mean, because 3/3 is 1, 4/3 is 3/3 plus 1/3. That's basically, well, come on. There you go. That's roughly 1.3, all right? What else? So x-intercepts -1/2 and -4. So -1/2, which is right here, and -4, that's right there. That's the x-intercept and the y-intercept. And the rest of the information, well, I mean, the fact of this about the symmetry, just look at the asymptotes. That's not going to give us any kind of symmetry, which we already found out analytically using the required process. So all we do now is plot the additional points that we got in the previous step. -5, -4.5, so that's a -5. -4.5, roughly here. And what's the other point? -3.5, -3.5, +6, and -2, -2, -6, and 2,6. So I think we already have all the required information to graph this. All right, let's go ahead and just connect the dots. It looks like this, roughly. All this didn't come out nicely. Well, that's the first part. And we have this part right here. Let me connect the dots first, and then I'm going to extrapolate a little bit. And this is roughly how it looks like. Notice how these dashed lines work like a guide to guide us through the shape of the to the shape of the graph of the function. Well, that's the rough sketch. All right. How about we look at this using graphing utility to determine whether everything we did here by hand and algebraically is consistent with the technology. So let's see. Let's give it a couple seconds first, and all right. So let me clear everything else. And again, because in this case we have more than one term in both the numerator and the denominator, when you use a graphing calculator, make sure to open parentheses every time you begin and open parentheses and close parentheses every time you open and close an expression. That is, in this case, 2x. So 2x squared is that plus 9x and plus 4. Let's close parentheses for the numerator. Division, open parentheses for the denominator, because in this case we have more than one term. If the denominator were only a sole x, well, don't need for those extra parentheses in the denominator. But in this case we need them for more than one term. That's x plus 3. And let's see the graph. Does that look like what we did? But again, recall that it's not going to show us that that vertical asymptote and that diagonal asymptote or slant asymptote. Well, we can plot the diagonal asymptote at least. Let me use the other version, and maybe this one. Hopefully we can see this dashed line like this. And what's that? 2x plus 3, right? Well, it's there, right? At least we can see this diagonal asymptote. I know there's a way to draw vertical lines, but I mean, at least we can see it. We can roughly see it. Again, yes, calculators are very, very smart devices, but they're not that smart. That's where we use our knowledge about the functions, our knowledge about asymptotes, and all that to complement everything we get from the graphing calculator. So it's it's all complementary. Algebra with technology and vice versa, right? Okay, so that being said, I believe we're essentially done with this topic. So let's briefly move on to the applications. So applications of rational functions. Well, notice the form. Oh, actually, there's a little typo here. There should be c of x equals mx plus b. I forgot to type the m over here as a coefficient, so just make sure to change it. And well, this linear function, this linear model, well, let's forget about rational functions for now. So, linear functions are the most common models to are the most common equations, yes, or models to model situations about business. Well, what do I mean by the business? For example, when you take a cab, for example, from the airport, you want to go home. So there is an initial fee, let's say $20. You pay $20 plus $2, $2 additional dollars per mile travel, right? That can be modeled by, I don't know, maybe 2x plus 20. 20 is the initial fee, and depending on the number, on the x number of miles that you travel, well, that's what. Or suppose you're running a business, for example, or for a fundraiser, for example. So you are investing, I don't know, maybe $50 in sodas, for example, in cans of sodas, and you want to sell each, let's say, also $2. I mean, maybe not too expensive, $2 a drink. And well, the end result will, in this case, be the revenue, which is the amount of money that you invest plus, well, actually the total cost. No, it's the total cost rather. The total cost, and well, it's what I'm trying to say is that in this case you are we're just finding the overall cost in this case. However, you want to know one piece of information that you want to know. It's the average cost when you divide that cost over a certain number of items that you sell, for example. And well, let's recall what the average is. So average, so for the average between, which is usually denoted x with a bar, the average of two quantities at x1 plus x2 and divide by 2. If you want to find the average of 4 elements in this case, well, add them all and divide them by 4. All right? You want to find the average of 17 scores, well, add the 17 numbers and divide by 17. But if you want to do this in the long run with a larger number of elements, well, you don't know how many elements, by the way, well, let's just call it x. So that cost, divide by the quantity x, which is the number of elements that you will be, or number of items that you will be selling, so to speak. Well, so that's the expression. That's how we will find the average cost. All right? All right. And that's because ultimately when you're running a business, say, you want to know some statistics about it. And in this case, this is where average or the mean, which is a more formal way to call it, that's where that comes into play. All right, so let's look at one example. So a cleaning service cleans homes. For each house call, the cost to the company is approximately $40 for cleaning supplies, gasoline, and labor. The business also has fixed monthly costs for $300 from phone service, advertising, depreciation of the vehicles, or if they're paying rent for the place where they're running the business from, etc. There's many expenses that are not listed in the situation, but you can think about all of them as well. And well, it happens that that's the value of this fixed costs. Well, so they're asking us to write a cost function that represents the cost in dollars for X number of houses per month. Well, let's start with C of X. That's going to be equal to X plus a number times X plus another number. That plus another number happens to be the independent term. And that independent term is related to the fixed cost to the company, which in this case is 300. And well, it costs $40 for every single call. That is 40 times X. So that's the linear model. Now they're asking us to find the average cost. That is C bar. Careful with the notation. Notice this bar at the top, that's to denote the average. Well, for now we're going to use the term average. Later, when you take probability and statistics, you will call it more formally the mean. All right? And that's C of X equals 40X plus 300 divided by X. And that's our rational function that we are going to work with. All right, so we're dividing by X to find the average cost. The cost of X amount could be 5, could be 7, could be 55, 73, I don't know. Your favorite number. Well, realistically speaking, and that's actually the next idea. So let's see, evaluate C of 5. And in fact, we have the graph of the function for our convenience, so you can see what's this going to look like. So they're asking us to evaluate for some values, that is C bar of 5. And let me do one calculation, 40 times 5 plus 300 over 5. That's going to be, okay, 40 times 5, is that a 200, I believe? That's 200 plus 300 over 5, and that's going to be 500 over 5, which is actually 100. And we can see that in the graph. When X equals to 5, what do we get? We get the Y value of 100. All right, so that'll be the average cost of having 5 phone calls. All right, so for C bar up to 100, C bar of 30. Wait, should it be 300 or? Oh, it's actually just 20, by the way, not 200. There's a little typo. Just 20. And C of 30, and C of 100. And well, without doing all these calculations, which is just plug and chug in this case, that's C of 20, that's a 55, that's 50, and 43. So what happens in this situation? So as expected, as discussed earlier, I mean, the more items that you sell or something, that all the average cost, and it's actually described over here in that definition box, the average cost per item will decrease actually as more items are produced, because of what happens that the fixed costs in this case are going to be distributed over a greater number of items in this case. All right? So, and well, so here is where we talk about realistically. Well, so, I mean, you cannot, I mean, if we think of the mathematical model, and if we observe the graph, notice this graph is approaching to some horizontal asymptote. That is like in the long run, I mean, for X really, really big, infinity, if you will. All right? That's what the mathematical model is it's depicting here. However, this particular mathematical model, it's used to denote a situation based on business. And here is where we need to put together the math versus the reality. And well, since in this case, X denotes the number of phone calls, would it be possible to receive infinitely many phone calls per month? I mean, Come on, that's not possible. So this is what they can do per month. So per month they can do 160 phone calls, and well, the thing here is. uh, if the number of calls were unlimited, what value would the average cost approach to? And what does that mean really in the context of the problem? Well, number one, again, we're talking about approaching infinity, but do you see this horizontal asymptote? What's the value of this horizontal asymptote? So that means that if the company were able to receive infinitely many phone calls, that means the average cost, which is distributed among these infinitely many phone calls and works at different homes, that means um, average cost approaches to $40. All right. And that's something that, well, when you are running a business, that's something you want to keep in mind, even though it's realistically not possible to sell infinitely many products. Of course, you guys as a business persons are bounded to limited supplies, right? But it's always good to see what could happen in the long run, right? And well, so this is the end of this chapter and section. Actually, it was quite of a long one, 15 pages of a handout here. But yet, like I mentioned before, pretty much every single, and as you could see on every single exercise, has its own particularity that is important to look at. Okay, guys. So let's see. I would like to briefly talk about. The next section. Well, come on, let's see if I can get a better color here. All right, hopefully it's easy to read. So I don't have a PDF file for this part, but I think it's we can make it through. So let's see. So we have these three graphs. So the question is, which of these graphs represent function? What about the first one? Does that one represent a function? Why? Oop, I was about to spoil it. Okay, why? Why is that a function? Yes.
Vertical line test.
Vertical line test, all right. So if we trace a vertical line, notice how that vertical line only crosses once on the function at every instance that you can think of. Well, I know there's like very steep values right here, but yes, it's still gonna pass it. We can guarantee that. What about the second one? Function or not a function? Not a function, right? It actually crosses more than once, and that this is kind of weird because if you think of the x-axis as the time and the y-axis as the position you are at, right? Is it possible to be in two different places at the same time? Can we be here in class at the same time? So at the same time we're at the beach or something? Well, we wish, but it's not possible, right? So that's one way to relate the definition of a function in a more real life situation. What about the third one? Function or not a function? Function, all right? Sounds good. Okay. Let me clear the red lines for a second. And let me focus only on the two that are functions. Well, actually, I'm going to come up with something different here instead. I don't know, maybe, yeah, something like this instead. Okay. So out of these two functions out of these two graphs that actually represent functions, furthermore, we can determine whether these functions are one-to-one or not one-to-one. And well, that has a lot of implications because from there, whenever we have a one-to-one function, that means the function is invertible. And if it's invertible, if we can invert the function, well, there's a bunch of pretty cool stuff that we can do. In fact, this will be the foundation to describe what will be next, which is the exponential and the logarithmic function. So, and there is a test to determine whether a function is one-to-one. Does anyone remember what's that test for one-to-one? I'll give you a hint. It's very similar to what we did before. Yes.
We'll use
The horizontal line test. And what does the horizontal line test say? Can you describe a little bit?
If it crosses through one just once, then it passes it, and it's one.
And it's one-to-one. But otherwise, if it crosses more than once, it's not one-to-one, right? Like in this case. Okay. Horizontal line, it crosses only once. Crosses only once. Crosses only once, right? Thank you, by the way. What about the second graph? Oh, look at this. Oh, it's crossing more than once. So it's not going to be a one-to-one function. All right, so let's denote that. 1, 2, 1. And not 1, 2, 1. All right? So, what does it mean? What's the formal definition, though, for one-to-oneness of a function? That means that if f of a is equal to f of b, then a equals to b, right? That's going to be our short. Let me keep it as short as that. You know. For example, I mean, if for some reason you happen to have the same point, well, that means the same A is equal to the same B. That's what our one-to-one it really means in this case. And well, let's go over some of the algebraic. Let me go over one algebraic example, like example 1. So, determine if f of x equals x plus x plus 2 is one-to-one. All right? So this is what we're going to do. So we're going to start with f of a equals f of b. That is, f of a equals f of b. So this is what we're going to do. The left-hand side of this statement I just wrote is asking us to evaluate the given function just a. I know it's a little weird because we are used to plugging numbers, and you know I hear that. However, well, we're going to work a little bit with symbols this time. That is, in this case, a plus 2 equals to. On the right hand side, we need to do the exact same thing on the function, but in this case we are going to evaluate at b. What's going to happen? Well, check this out. Notice how if I subtract the 2 on both sides, they both cancel, and a equals to b, which in this case, this is what we wanted to show, because if f of a equals to f of b, then it has to be true that a equals to b, which is the situation. And you might be thinking, well, why is this important, or how this makes sense? Well, to make more sense out of this, how about we do the graph? So the y-intercept, which is 2, and the slope, which is 1. Oops, wrong. So that's the diagonal line. And if we look at the graph of this linear function, do the horizontal line test, it's going to pass the horizontal line test. So in this case, we're putting together both the formal definition of one-to-one functions versus the horizontal line test. Let's do one example in these last few minutes in which it's going to fail. So example number 2. For example number 2, determine if 2x, f of x equals to 2x squared plus 5 is 1 to 1. But in this case, we're going to do it algebraically. Well, I know you can already tell this is going to be a no because you're looking at the second power on the variable x, and you know that this is going to describe the graph of a parabola. Well, thinking of a parabola, of course, we already did that example, fails the horizontal line test. But we need to do this formally, algebraically. Let's go ahead and do that. We're going to start with the statement if f of a equals to f of b. All right, that is, on the left-hand side, evaluate the given function at a. That is, whenever you see the letter x, replace with b. I mean, with a. That's a 2a squared plus 5 equals to 2b squared plus 5. Let's do some simplification. That is, subtract 5 to both sides. That's gonna leave us with 2a squared plus b squared. Oh, no. 2b squared. Divide both sides by 2. And that's going to leave us with a squared equals to b squared. And well, at this point, it seems like it. However, check this out. So I would like to solve for a. So to solving for a would imply to use the square root property. And well, I'm going to make a silly mistake over here to see if you can catch it. A equals the square root of b squared, and a equals to b. And well, yeah, apparently it's 1 to 1, isn't it? But hey, I did a mistake. What's the mistake I did here? Yes.
You did square root
Oh, yeah, well, that's, okay. Yeah. Let me write it like this. So, yeah, that's A. But I'm still on a mistake here. What's the mistake? Yes. The plus or minus, right? The plus or minus. So, plus minus, plus minus, plus minus. And in this case, what's the implication in the end? Well, this implies that A equals to negative B, but also A equals to B. That's where we conclude it's not 1 to 1. It's actually 1 to 2, all right? So, yes, this parabola, y-intercept at 5. Yes, it's still a function. We hopefully we all agree that it's still a function. It passes the vertical line test and the like. However, the idea of a function not being 1 to 1 is that we are getting the same y value, which is fine, for different values of x, which is still fine. It still checks with the definition of a function. So, for example, when it's not a function, you cannot be in two different places at the same time. But the fact that a function is not 1 to 1, which is still a function, it is possible to be in the same place at two different times. For example, you can be in this class at 12 p.m. and maybe you can come later at 5 p.m. for another class. That's still a function, but it's not 1 to 1.